Hi everyone. Magnification is an important requirement in the field of any science subjects, especially in biological sciences. Magnification can be achieved by the use of microscopes. And we cannot think a biology lab without a microscope. The first picture that comes to your mind when you think about a biology lab is a microscope. So, such an inevitable role these microscopes have in biological labs. The diversity of these microscopes, it ranges from a simple magnifying lens to complex instruments like electron microscope, confocal microscopes, etc., which are very complex in their instrumentation and working procedures. And these microscopes can be classified into two, that is, optical and non-optical. The compound microscope, which the students use for their routine work in their biology lab, it is an optical microscope. And these compound microscopes, they are called as compound microscope since they use more than one lens systems. And let us see the important parts of a compound light microscope. This is a compound microscope and it has two important optical parts. The first one is the objective lens. It gathers light from the object that is placed on the stage of the microscope. And the second one is the eyepiece. The eyepiece gives us the image of the object. Then the image is formed by the light emitted from the object that is placed in the microscope. And in order to know how an image is formed, you must know some basic informations regarding the ray diagram for an image. Let us see how the ray diagram is constructed. So this is a convex lens, and this convex lens is having a center point called optic center. Then an imaginary line drawn through the optic center is known as principal axis. Now this lens forms a part of a sphere or a circle, and the center of that sphere is designated as 2F or center of curvature, and the distance from the half distance from the optic center to 2F, it is designated as focal point, or it is simply named as focus. Then this convex lens, it forms a part of two circles or two spheres, and hence it has two focal points on either side of the lens and 2F. Now we are placing an object at 2F. Then this object produces light from all part of this object, and we are not considering all the rays produced by the object. We are taking 2 or 3 representations. First, a light ray which is passing parallel to the principal axis. It reaches the lens, then the path of this ray is deviated. Let us see how it is deviated. See, after passing through the lens, it deviates and passes through the focal point. Then another light ray which is passing through the optic center. Let us see what is going to happen to this ray. See, it is passing without any deviation, that is, it is passing straight. Then the third case, that is the image, the ray is passing through the focal point on the same side. So, after passing through the lens, it travels straight. That means it is traveling parallel to the principal axis. So, these are the three representative rays that we are considering for image formation. We need two of these rays for construction of the image. Okay, see here we are placing an object at 2f. This ray which is passing through the lens in a parallel manner, it deviates and it travels through the focal point. Second one, passing through the optic center, it passes in a straight path. So you can see these two rays, they are converging at a point. Here the rays are converging and you will get an image at this converging position. See, that image is formed at 2f on the other side. Let us compare the object and the image. See, the image formed on the other side, it is of the same size. Then the image is inverted. It is upside down and it is a real image. A real image means the image is formed by the intersection of the two rays coming from the object. So this is how an image is formed when the object is placed at 2f. Let us take the second case, that is the object is placed at f, that is at a focal point. So the light ray is traveling parallel, then it deviates and it passes through the focal point. The second one, it is passing through the optic center and it is not deviating. Here you can see that these two rays are not converging at any point after traveling through the lens. That means here we cannot see an object, image. That image is formed at infinity. Then the third case, here we are placing the object between f and 2f. Let us see what is going to happen if we place the object here. See, the first ray, it is passing through the focal point. Second one, it is traveling straight. And here you will get an image beyond 2f. And see, the size, the image is highly enlarged. At the same time, it is inverted also. And the image is real. That is, it is formed by convergence of the two rays. Then here we are placing the object between the optic center and focal point. See, here the rays, after traveling through the lens, it is not converging, it is diverging. That means there is no possibility for the two rays to combine or to converge at a point. So naturally you may think that there won't be any image, but see, you can see that if you look from the other side of the lens, you can see that these two rays are coming from a point on the other side. You may think that there is an object at this position and the light rays are coming from that point. So an image is formed at this position on the same side of the lens. And here the characteristic features of this image, it is different. Let us see what are they. So here the important thing is that here the image is not real. It is virtual. No convergence of the rays happening here. It appears only to come from this point. Then the image is highly magnified. Here we get the maximum magnification and the image is upright also. So these are the different positions at which we can place the object. Now let us see how an image is formed in a compound microscope. As I have already told, the compound microscope, it has combination of lenses, more than one lens systems. Okay, so this is the first lens system, that is the objective. Then we are placing the object between F and 2F. So you are getting a magnified image on the other side, that is beyond 2F, and this image forms the object of the second lens, that is the eyepiece. So here the magnification of the first lens, it is still magnified with the second lens. Let us see how is it possible. So this is the object that we have placed. Then this is the first image formed by the objective lens. See, it is magnified. Then we are placing the second lens, that is the eyepiece, and here the image formed by the first lens, it is placed in such a way that it lies between the focus and optic center of the second lens. See, here, as we have already seen, the light rays, they are diverging, but it appears to originate from this point, and there you will get a highly magnified image. And here, even though the object is placed upright, we are getting an image which is upside down, but the object when placed between F and optic center will produce an upright image. But here this image, which is the object for the second lens, that is inverted, so you are getting a similar inverted image after magnification. So we are placing the object here, a small object, then the object, it is magnified by the first objective lens, then again it is magnified by the second lens, that is the eyepiece, and we are finally getting a highly magnified image. So this is the basic principle behind magnification in a compound microscope. Here you can see that the final magnification, it is the magnification of the objective lens and the magnification of the eyepiece added together. Say for example, if the magnification of the objective lens is 10x and the magnification of the eyepiece, it is 40x, then the final magnification will be 10 into 40, that is 400x. So you can have a final image which is magnified 400 times than that of the object placed in the microscope. So this is the basic principle of magnification in a compound microscope. So I hope you are now thorough with the basics of magnification in a compound microscope. So thank you.